Imagine you're stranded on a huge, massive beach and you're looking for one specific seashell. That's gonna get you out. Now, turn the beach into the internet and the seashell into your specific bit of information that you're searching for. That is what a vector database can help you with. Welcome back to another episode of the Scripting Them podcast. I'm Fernando, your host as usual, and in this episode we're going to be talking about vector databases. Not specifically about one product or one use case, but rather what they are, how they work, and most importantly, why is everyone and their mother talking about them? In other words, why are they so popular lately? So let's go. So first, what is a vector database? A vector database is essentially just a NoSQL database. It's a specialized database that takes your vectorized information, stores it somewhere, and then allows you to perform some geometric-based operations. Why vectors though? And that's key, actually, the moment you understand the concept of a vector. And a vector is just a list of numbers, let's put it that way. The meaning that we give to these numbers is what makes them relevant. If we think about vectors or just this list of numbers as a set of coordinates in a multi-dimensional space, then we have the ability to perform some interesting operations between these vectors, essentially. For example, finding the vectors that are closest to other vectors, finding the ones that are within a specific quadrant, or things like that. The point here is that we always have to think of them in a multi-dimensional space. And what is a multi-dimensional space? It's just a fancy way of saying a space that has more than 3 dimensions. If we think about 3 dimensions, we can easily see this in our heads. Just think of your vectors as just having 3 numbers, which is hardly ever going to happen in these databases. But if you reduce the problem space into just 3 numbers, you can think of each, as a different axis in the 3-dimensional space, X, Y, and Z. And then your vector essentially points to a specific point within that 3-dimensional space. Now, if you were able to transform whatever piece of information that you have, whatever piece of data that you have, and put it and transform it somehow into these 3 coordinates that uniquely identify this piece of information, then you have a way to locate that information within your 3-dimensional space. Now take another piece of information, do the same thing, and put it within that same 3-dimensional space. Now, what happens if those 2 points are close to each other? What does that mean? And that's kind of where we're going now. Before we move forward with that line of thought, let's go back a little bit and to the concept of a vector and why vectors, essentially. Why do we really care about vectors? If you think of relational databases, the usual SQL database, those are fantastic when you have columns of data, essentially, columnar setup, where you have records, all of these records having the same columns, and within those columns you have specific properties of that record. That's fantastic. We all know about that. But what happens when you're dealing with data that is not easily translated or saved in records, columnar records like that? For example, just the faces or the sentiment that someone has inside a picture. Those are more complex pieces of information that are either inside more complex data or just essentially not structured data, right? Like an image, like a video, like an audio file, for example. Or they are insights that you get from analyzing a piece of information, maybe reading a tweet and getting the insight out of that, or getting other bits of input or output from analyzing something that could be structured, but the data that you get out of is not. That is where vectors come in handy, because vectors are just a representation of those insights, of those images, those audio files. Somehow, and that somehow is going to be key, they are translated. That non-structured data is translated into structured data, essentially, into a vector that just by looking at it, you, a human being, cannot really make sense of it. They're just floating point numbers, right? It's just a combination, maybe 100, 700 numbers that to you, they don't really make any sense. But within the context of a vector database, they make a lot of sense and they are actually very useful. Now, the key to using these databases for something useful, and we're going to be looking at some of these use cases in a second, is the how of how you turn that data into the vector, essentially. They're known as embeddings. The vector format of a piece of information is an embedding. Maybe you've heard of that term when using ChatGPT, for example, or some other LLMs, or even the same happens with generative AI. And when you're using something like Stable Diffusion to create, from text to image, you can train or specialize those models using embeddings. Now, what is an embedding? The embedding is just that. It's just a combination of numbers that add extra information, extra context to the neural network that is working underneath everything. The key, again, is how you create those embeddings. The vector database by itself is not really able to do anything meaningful, let's put it that way, before you insert the data inside it, right? So the process of turning an image into a vector or an embedding is the key where you load that embedding with meaning, right? So it all depends on what you're doing, essentially. If, for example, you're trying to create a face similarity search, for example, I'm making this up, but that could be a use case. So the process of creating the embedding from the pictures will have to look at the image, and it will have to get the specific features of different faces inside the image and translate only those into the embedding. And that is then what gets loaded inside the vector database, and that is the meaning of it. So essentially, if remember at the beginning of the episode, I said, what happens if you have 2 points that are close to each other? In this case, if you're looking at an embedding that contains information about faces, then that would mean those two faces, right, are similar to each other. So if you were to be creating some sort of face similarity search, you could, based on the embedding of your input image, you could find all other points in that multidimensional space that are close enough to yours, and then those points would be linked to images with faces that are similar to your input image. See where I'm going here? Same thing could be if you were to analyze a piece of text, for example, a book, right? If you were going chapter by chapter and turning each chapter into an embedding, what do you get out of that chapter? For example, you could get the overall meaning, the overall message. You could get a lot of insights from analyzing that text and then turning that insight into an embedding. And then you go in and you have a library of books being analyzed that way. And you suddenly say, well, I remember something about, I don't know, the meaning of life. Then you turn that sentence, the meaning of life, into an embedding. And I'm just, the examples at a very high level, and I'm skipping over a lot of details here. But the point is, you would turn that meaning of life sentence into an embedding, and then that embedding would go into that multidimensional space and say, well, all the other points that are close to mine are probably talking about the meaning of life as well. So you can grab those references and reference back either to specific chapters or specific books. In other words, you're essentially creating sort of a semantical search. The key, again, and I keep repeating this, is the algorithm that you use to extract that insight and to turn that insight into an embedding. Without that algorithm, the vector database is just nothing, not that interesting, not that useful. But the moment you load that vector with meaning, then finding the nearest neighbors, for example, for a specific vector, has a lot more meaning, has a lot more value. Another use case, and this one is probably very close to everyone, is using Netflix every day, right? Maybe you don't have the Netflix account, but everyone knows how Netflix works, and you know that once you log in with your user, you get a list of recommendations from Netflix huge database that are tailored to you, are somehow tailored to your liking. And obviously, one of the main things that we tend to believe is, well, I watched all these sci-fi movies, so obviously this is going to be giving me some sci-fi titles as recommendations. And that's a good approximation. But if you think about it a little bit harder now with this context, you could be adding a lot more. You could be adding this genre of the series or movies that you watch, but also the list of actors. You could be adding your own genre. You could be adding your age. You could be adding even the country that you live in. All that information that actually Netflix has on you, and then creating sort of a profile of you, right? And turning that into a vector. So it's not just about saying, Well, Fernando actually likes sci-fi, so let's just grab all these sci-fi movies and throw them in his face. He might not like all of those because he might not like the actors or actresses there. He might not like some of them might be too old, some of them might be too new for him. If you add more data points into that profile and then turn that into a meaningful vector, then you might say, well, this movie with these people inside it is located here within this multidimensional space. Fernando is actually close to that point. So let's recommend that point to him as well. Those points, essentially those vectors in this multidimensional space, they're not fixed, right? Specifically, those that are related to a profile. I might start liking things. I might find a genre that I've never seen before. So I might actually start moving away from my initial or starting point and moving into other spaces where there are other movies. The point here is that recommendation system that you're seeing on your everyday, for example, could be powered by a vector database. That's all what I'm trying to say here. That's where I'm trying to go. You could be interacting with vector databases everywhere and you just don't know. There are many ways to create a recommendation system, for example, so don't quote me on that. I'm not saying Netflix actually is using a vector database, but they could be, because it's a very valid use case for this technology. Again, on their own, vector databases are just great at storing vectors in this multidimensional space and then giving you a set of geometrical or multidimensional functions to find closest neighbors and some other operations, but they're not really useful or meaningful on their own without you loading those vectors with actual meaning. And now, why do you think I've been talking about face similarities. I've been talking about like semantic search. I've been talking about recommendation engines. Those are not necessarily new technology or new features on complex systems like Google, for example. So they're not new. They're not things that are revolutionary right now. So why is everyone really talking about vector databases these days? One of the newest use cases, and probably one that has been popularizing this technology lately, is the use of vector databases with LLM to achieve what is known as RAG, or Retrieval Augmented Generation. So if you've been using ChatGPT, for example, you know that you can upload a document, a PDF, for example, to ChatGPT and start asking questions about it. There are other LLMs that allow you to do the same. If you're using open source LLMs, there are products like LM Studio that will let you do also that. They will let you upload files, text files, PDF, and so on to your LLM, and then ask questions and ask it to use the information inside them as context for your questions. Essentially, you're not training an LLM. You can't really train an LLM that's fixed, but you can fine tune it or add extra context and use RAG. Now, the way RAG works is you upload that extra context to it, and it doesn't really go to the LLM. Obviously, you can't really do or affect the LLM that way directly, or its internal weights in the neural net. But what you can do is you can vectorize that information. Again, if it's text we're talking about, probably gonna be vectorizing the semantic meaning of pages or sections of your document, and then turning that into vectors that are going to be stored within a vector database, a local vector database. Now, when you perform a search, asking questions about it, what the RAG process is going to do is it's going to vectorize your prompt, your question, and then it's going to use that vector database to find the closest embedding from your document and say, well, if this is the closest point that I can find, or these are the closest points that I can find to the prompt, then I'm assuming the context inside those sections of the document are meaningful to the question. So the RAG process is going to add that context, add it to the prompt, and then send it to the LLM. It's kind of cheating, if you will, because the LLM doesn't really have that information, but because you're giving it as part of the prompt, then you're somehow giving it the answer to your question, or at least you're giving it the content that has the answer to your question so that it can process it and give you the answer. That's roughly at a high level how RAG works. And it's a nice trick actually, because it allows you to split large documents into meaningful parts that can be vectorized. And then, if you provide the right prompt, then it will be able to grab the semantic meaning of your question, whatever you're trying to ask about, and then it will find that in that multidimensional space, and then give it to the LLM to simplify it, to go through it, and give you the final answer. That's probably the most common use case for vector databases right now, and that is why everyone's talking about it. That's kind of answering the question from the beginning of this episode. Why is everyone and their mother talking about it? Because they're very related to LLMs. They're very related to ChatGPT and to other LLMs like it. And they actually make them very useful, because a general LLM is fantastic to answer general questions. But if you're trying to specialize that LLM into a specific area, or you're trying to ask questions about something that is new, something that happened, or was some sort of content that was created after it was trained, the LLM is not going to have enough information about it. So it's a very fast and cheap way to give it that extra information without you having to spend who knows how much money into retraining something that some of these are just way too expensive. They require way too complex hardware for you to actually do it in your own home, or fine-tune it, which is also a more complex process and also requires a little more time. So you can use RAG within minutes if you have the right hardware in your local machine, or on with cloud services. The actual ChatGPT version, it just uploads and you get the answer back within the normal time frame, so within seconds. It doesn't really generate a delay or any kind of problem essentially with the performance of it. So again, great way, cheap way, fast way to sort of quote unquote train or specify your LLM into something that wasn't really trained before. And there you have a really short episode coming back after sort of a month without generating anything. I've been kind of busy with work and life in general, so sorry about that. But hopefully this video and this episode is useful, interesting, and relights your interest in the podcast. So remember, vector databases by themselves are interesting, right? Mind you, they're quite a nice piece of technology, but on their own, they're not really magical. They're not really useful unless you load some sort of meaning into the vectors that you put inside. So that way, close enough vectors, or within vectors within a specific quadrant of that multidimensional space, they mean something, right? They have some sort of relationship. Otherwise, they're just points or vectors in a space that means nothing. So you can do tons of it. Remember, you can do a lot of things with these vectors, from recommendation engines to specific searches, to the point of actually expanding the knowledge of an LLM using RAG. Now, as an added bonus and as an added piece of information, I do have one specific course on LinkedIn Learning about using Redis as a vector database, which is cool on its own. But I do cover examples of how to use a vector database to create a semantic search and to create an image similarity search. Very basic ones using Node.js in the backend, and Redis again as the vector database. So if you're familiar with Redis but didn't know you could use it that way, check it out. It's not really a long course. It just covers kind of a little bit more detail into what I covered in this episode, and it gives you two actual very practical examples of, you actually have access to the code as well. Two very practical examples of how to achieve that. You have working code when you get the course, and those projects will actually, they will work with vector databases and will perform that semantic search, or the image similarity one that I really found interesting and fun, because the output that you get is very powerful, and it doesn't really take a lot of knowledge, or it doesn't really take a lot of time to create it. So you get a lot of value from a very small investment. So I'll make sure to link the course in the show notes in case you want to check it out. And that's it. I hope you found the episode interesting enough, and that you would share it and subscribe if you haven't yet to the podcast or to the YouTube channel if you're watching this in YouTube. I hope I made this new edit format interesting, or more interesting at least than previous ones. And that's it. Thank you again for watching or listening, and I'll catch you on the next one. See you around. And that was it for this episode of the Scripting Them podcast. Thank you so much for listening. Remember that you can find me online on Twitter at TheDeepMan123, and you can also find the podcast YouTube channel just searching for the Scripting Them on YouTube. Thank you again, and catch you on the next one.